So we started looking at probability, and if I remember correctly, I think this is actually where we got up to, probability with independent events. Okay? And we actually said that, and basically I did define independent events last time. Two events are independent, okay? If the probability of one of them happening is not affected or does not depend on whether the other event occurred or not. I think what we actually said was event B, I think we said is independent if event A, the other one, does not affect the probability of event B. In other words, if the probability of event B occurring or not, the probability of it is not affected or does not change whether A has occurred or not. Okay? Now, if events A and B are independent, what's nice about it is, as you can see here, we can more easily calculate the probability that they both occurred. We can calculate the probability of both of them occurring. Okay? Namely, the probability that they both occurred, the probability of A and B, that's just the probability of A times the probability of B. That's what it is. Okay, so in other words, we just multiply their probabilities together if they're independent. Okay? If they're independent. They're not independent, then that formula is not going to work. In fact, let me do an example with this. So here we're tossing a coin into the air twice, okay? We toss it, we see what the coin lands facing up, if it lands heads up or tails up. Then we record that. Then we toss the coin a second. And we see if it lands heads up or tails up, okay? That's basically what we're doing here. We want the probability that the coin will land heads up both times. We want to see the probability that the coin will land heads up both times. Well, keep in mind that these events are independent. What we toss the coin, and no matter no matter if it lands heads up or tails up, we're going to toss the same coin again. So whether or not the coin lands heads up or tails up first, that's not going to make a difference that's not going to make a difference with whether it lands heads up or tails up the second time. It's not like if it lands heads up, then we have to toss the coin a certain way, or if it lands tails up, we toss it another way, if that makes sense. What I'm trying to say here is that both events are independent, first and second toss. So the probability that the probability on the first toss lands heads up, right? Well, both, heads and tails are equally likely, so it's 1/2. Same thing with the second toss. The probability that the coin lands heads up on the second toss is again 1/2. Okay? Again, both events are independent. So in this case, events A and B, where A is that the coin lands heads up on the first toss, B is that the coin lands heads up on the second toss, both of them have the same probability. So really here, we're using this formula. These, A and B, okay, A is the event that the coin lands heads up on the first toss. B is the event that the coin lands heads up on the second toss. The probability of A and B is just the product. Get 1/2 times 1/2, which is 1/4. Okay. Again, I know I didn't really write like a math proof, so to say, that they're independent, but if you think about it, yeah, they're going to be independent. You know, whatever you get on the first toss, that's not going to affect what you get on the second toss. And even to really drive that idea here, sorry. The probability we get then is the product, which is a fourth. So they both occur. Excuse me. Here, okay, I'm basically solving the same exact problem. But what I'm doing is I'm just looking at the sample space. You know, you can't always do that, but here we can. There's not too many outcomes in total. But again, here's what happens. This is the event that we get heads. Excuse me, this is the outcome of getting heads on the first and second toss. Here we get heads first, the coin lands tails up. Here the coin lands tails up first, then the coin land heads up, and so on. This is what we get. So these are all the outcomes. They're all equally likely. And so by looking at the sample space, right, we can see that the event, the coin lands heads up twice here is 1 out of 4. You know, there's 4 outcomes in total, and only 1 outcome corresponds to what we're looking for. So that's what we get. So again, the probability is 1 out of 4. So, you know, just another way to see that we're right. That's all I'm trying to do. All right, that's good. Okay, so we know what to do if A and B are independent. What if they're not independent? You know, what if we want the probability of 2 events occurring at the same time, but they're not independent? I mean, if you went back to that, I think it was that marble example we did last time. You have a bag of marbles, right? I think there's 10 red, 5 blue, and 8 black, or something like that. Right? We reach in, we take a marble, we note the color, we don't put it back, but we reach in to take another one. Well, the event that the first marble is red and the event that the second marble is red, those events are not independent. But what if we wanted the probability of both occurring? Well, this is where we have to use conditional probability on an example like that. So I was trying to cite an example from last time where the events were not independent. Excuse me, not independent. If we wanted the probability of both occurring, we would use this conditional probability. So here, this is just basically notation. This says the probability that event B occurs given that A occurs. That's what this is, as you can see. The probability that event B occurs given that A has occurred. Or you can think of it this way. The probability that B occurs such that event A occurs. That's another way to read it. What they call conditional probability. So in this case, you're taking into account another event occurring. So this is probably what we're gonna use when A and B are not independent events. Because in that case, you have to take into account what the other event occurring. And before we do that, let me just put this here. They're not commutative. In other words, if you do the probability of B given A, that does not have to equal the probability of A given B. You know, they could equal, but they don't have to be equal. So we can't assume they're equal, is what I'm saying. I want to say this also. It's possible that A given B may not even make sense, but B given A does. So. Also, if you went back to our definition of 2 events being independent, you know, A and B, And if you actually were to write out those definitions using our new terminology here, using our new notation, this conditional probability, you would have this. Namely, A and B are independent events. If they are, then the probability of A equals the probability of A given B, right? And that's also equal to the probability of A given that complement of B. In other words, if A and B are independent, right, the probability of A occurring is not affected if B occurs or B does not occur. So the probability of A occurring is not affected. It's the same if B occurs, hence the probability of A equals the probability of A given B, of A given that B occurs. But if B does not occur, it doesn't change either. So it's also the probability of A given the complement of B. Remember, this B bar here stands for the complement of B. You know, if you have a bar here over the event, that means the complement of the event. That occurs if the event does not occur. Okay, you know, the event occurs or its complement occurs, not both. Okay, so given that B occurs, the probability of A occurring is not affected. Same thing with the complement. If B does not occur and its complement occurs, you know, that does not affect the probability of A occurring if A and B are independent. Here's the same thing, is basically interchanging the roles of B and A. That's all. Okay. You know, it's just a consequence of our definition, is what I'm saying here. Let me stop the recording.